Okay, now that we've talked about electrons in individual atoms and ions, we're going to start talking about electrons in covalently bonded molecules in Chapter 7. So without any further ado, we'll go ahead and jump into that. So just to remind you, a covalent bond is a bond that exists in a molecule, as opposed to an ionic compound, that results from sharing electrons between two atoms. And this is normally at least 2 electrons. 2 is the most common number, sometimes 4, sometimes 6, very rarely some other number other than those. But in a covalent bond, what we have are attractive and repulsive forces involved between the two atoms, and these need to be balanced out. So between each atom, we have a nucleus in one atom and a nucleus in the other atom. Those are both positively charged, so they're going to repel each other. Likewise, the electron clouds on both atoms repel each other because the electrons are negatively charged. However, there's also attractive forces, namely between the electrons of one atom and the nucleus of the other atom. And so we've got 2 of those involved since each atom has its own electron cloud that can be attracted to the other atom's nucleus. Now, both of these forces depend on the distance between the 2 atoms. So how can we determine what this distance is? If we look at this chart, this will give you a good idea of what determines this. So on the x-axis here, we have the distance between 2 hydrogen atoms in a bond between 2 hydrogen atoms in a hydrogen molecule. And on the y-axis, we have the potential energy associated with that. So what determines the distance between the 2 hydrogen atoms in this bond is going to be whatever distance between them that minimizes the potential energy, because physical systems will try to minimize their potential energy whenever possible. If we have the 2 hydrogen atoms very far apart relative to the bonding distance, we're not going to have much in the way of attraction or repulsion between the 2 atoms, because electrostatic forces like the attractive and repulsive forces involved are stronger over shorter distances. So when the atoms are far away, not much is going on between them. If we bring them closer together, so we move to the left along the x-axis, you can see the potential energy starts to go down, and it keeps going down until we get to this point that's labeled on the graph as the bond length. And it happens that for a hydrogen atom, or a hydrogen molecule, I should say, this happens at a distance of 74 picometers between the 2 atoms. And this is 436 kilojoules per mole lower in energy than the 2 atoms being infinitely far apart. And this is the optimum separation between the 2 atoms because it minimizes their potential energy. If we try to bring the hydrogen atoms even closer together than that bond length of 74 picometers, they're going to start having repulsive forces between them that are too strong, and the potential energy will start going up again. Now, this optimum bond length is dependent on what 2 atoms are involved in a covalent bond. So 74 picometers is the distance for hydrogen, but since hydrogen atoms are pretty small, that is relatively short compared to most bond distances. On this chart here, there's a list of some example bond lengths. You should definitely not memorize these or anything, but it will at least give me an opportunity to briefly go over some of the things that affect bond length. Now, the bond length, to a large extent, is just determined by the size of the 2 atoms involved in the covalent bond. So the larger the atoms are, the longer the bond will be generally. Now, the significance of bond length, besides everything that I just discussed, is, to a rough approximation anyway, the shorter a bond is, the stronger that bond will be. So a longer bond is generally a weaker bond. A good way of illustrating this is if we look at, For instance, a carbon-carbon single bond, which is right here, versus a carbon-carbon double bond, versus a carbon-carbon triple bond. Now we'll talk about what single, double, and triple bonds mean later on, but we can see that a carbon-carbon single bond is 154 picometers, and a carbon-carbon double bond, which is stronger than a single bond, it's about twice as strong in fact, is only 134 picometers, so it's a shorter distance between those two atoms. And a carbon-carbon triple bond is shorter still. It's only 120 picometers.